In this video, we'll be beginning our final lecture set, that on regression. Now, regression is an extraordinarily large topic, and in fact, it can really contain most of what we've talked about thus far in this class. So, we can't cover regression in a single week, and frankly, we're going to try to do it in 2 or 3, and that's going to be pretty tough, and we're not going to get to even close to everything. But hopefully we'll hit some of the big highlights so that when you go out, if you're asked to look at one of these relationships, you'll be able to. Now, to try to make this a little bit more accessible, to go a little bit slower, we're going to break this down into a couple of different, I'll call them sub-lecture sets. Your textbook actually has completely different chapters for these. The first one will be simple linear regression. And simple linear regression, simple just means that we have two variables, a independent and a dependent variable. Linear is something that we're never going to talk about deviating from, weirdly. And in the simple linear regression case, it kind of means a line, but not really. We'll talk more about that when we get to multiple linear regression. And regression is the process of regressing one variable on another. Ultimately, we're looking at the relationship between two variables. Now you can see we've got a whole bunch of different things we're going to cover just in the context of simple linear regression. We're going to have a similar number that we're going to cover in multiple linear regression, but hopefully by starting with the simpler case and then moving to the more advanced case, it'll help us to put together some pieces over time. So when we're looking at the relationship between a bunch of different variables, simple linear regression and regression in general is often very, very useful. Now, in this simple linear regression, we can talk about how this roughly deviates from the variables and methods that we've discussed before. So sometimes it's nice to have a matrix, and then we have a DV listed and an IV listed. And remember at the beginning of class we talked about their types. So let's say we have a categorical variable and a continuous variable, and then a categorical variable and a continuous variable. So categorical and categorical, we had this chi-squared analysis. For the dv being a continuous variable and the iv being a categorical variable, we had ANOVA, or the specific case of ANOVA with just two groups. That was a t-test, and I'm sorry for my terrible handwriting here. Actually, that's probably as good as I'd ever do. And then for the continuous IV and the continuous DV, this is where we are right now with regression. Oh my gosh, that's a really bad reg. Actually, something that we're never going to talk about is the continuous IV and the categorical DV. This is called a logistic regression. We might touch on that at the very end of the multiple regression chapter. Excuse me. But it's actually something that we're not really going to focus on. This would be something for maybe a second level regression course, where we have this continuous independent variable and the categorical dependent variable. For now, for this class, if you came across this and really needed to analyze it, remember that we can always go in this direction. That is, we can always go from continuous to categorical, though we can never go from categorical to continuous. So if I had a continuous independent variable and a categorical dependent variable, I could categorize my continuous variable to make it so that I have a categorical independent variable and a categorical dependent variable, and then run a chi-squared if I really needed to do that using the tools in this course. There is an appropriate tool, again, for doing continuous independent variables and categorical dependent variables. In fact, there's a couple of them. Logistic regression is one, and discriminant analysis is the other. In any case, what we're largely talking about is going to be in this cell, the continuous outcome and the continuous independent variable. Now what's interesting, and what we'll talk about as we get more advanced, is actually we can kind of sneak into the ANOVA cell with regression too. What we really need with regression is a continuous outcome, but we can actually end up handling categorical and continuous independent variables with regression. So regression is going to end up being this entire bottom row, which is again why I say it covers so much of what we've done in class, because t-test, ANOVA, all of that can fit in with regression. Now for the notation, this dependent variable, or the outcome, is going to be called y, and the independent variable is going to be denoted by x. So we're going to have an equation eventually that's going to have y on the left side, and then somewhere over on the right side is going to have x, and then we're going to have some other stuff that's over here too. But we're saying x ideally affects y. Now note that the regression model doesn't say that. I think we've talked about this in previous videos, that the direction of causality is not necessarily established within any statistical method. It's established by the research. But if we were trying to assume causality, the causality that we'd be trying to address using this model would be x causes y. And again, that depends on your research setup, but sometimes it's good to know, to think about even when you don't have causal models. So if I'm trying to predict, say, how well your income affects your eventual health outcomes later in life, then I might say income on health outcomes is what I'd be looking at with this particular model. Income being the independent variable, that which affects something else, and health outcomes being the dependent variable. And I might look at this without using a method that allows me to make causal claims, but even if I'm looking at this observationally or correlationally, I can still think, hey, I'm trying to see if income affects these health outcomes. So I'm looking in that direction, and that's what tells me income should be my independent variable and health outcomes should be my dependent variable. So for simple linear regression, we have one independent and one dependent variable. And I don't mean to keep a curtain over your eyes. This isn't intended to be a big mystery. For multiple regression, we're going to have more than one independent variable. Just like with one-way ANOVA, we had one IV and one DV, and then we moved on to factorial ANOVA or two-way ANOVA. Factorial is generic, two-way is just with two independent variables, where we had two independent variables and one DV, or three or four or five if you wanted to get more and more and more. We didn't talk about that in class, but you absolutely could. Multiple regression is the exact same way. Multiple regression, we just have more than one independent variable. And again, we'll start with one and then build up to that later, that later more advanced model once we get the hang of doing this with just one. Now, in the simple case, we have a straight line. Note, and this is going to be a bizarre mind twist, that in multiple linear regression, we can model curves with linear regression, and we'll talk about how to do that. But in simple linear regression, we're typically going to have a straight line. And we talk about it right here. We have multiple variables. It's going to be called multiple regression. Specifically, multiple independent variables. We're not going to even address the multiple dependent variables case, though there are methods that do address that. All right, so when we're looking at how y is related to x, and I'm not going to really make a distinction. Your textbook distinguishes between the model and the equation. I'm not going to worry about that too much. What I will say is that for the model, when I'm looking at a particular individual's outcome, this is important, so maybe jot this down on your notes if you're following along. When I'm looking at an individual's outcome, I have a structure, and actually these two pieces together are what are going to make up the line. So I have a line when I'm looking at an individual's outcome. That's a very bad line, but you understand what I'm saying. And then I also have an individual's variability from the general pattern. So this line is the general pattern across everybody. And then an individual's particular point might not be exactly on the line. So whenever I'm looking at an individual outcome, it's important that I recognize I have a general pattern that fits everybody pretty closely. But then I also have an error term, which allows me to represent the fact that an individual's observed outcome is not necessarily exactly on that line. So this is important. So this overall pattern is kind of on average, and we can directly represent that. We'll talk about that on the next slide. Now you'll hear me talk about beta 0 and beta 1 as parameters. Now parameter, remember from our previous statistics course or from earlier in this class, depending on when you first covered it, parameters regard the population. So these are, if I had all of the data in the population, I would know this beta 0 and beta 1. I don't, so I will never know these. What I will eventually have are statistics that estimate these, sometimes called parameter estimates, based on a sample, and that gives me hopefully a good guess at these values. But I'm never going to know beta 0 and beta 1. That's the perfect population line. I'm just going to have a hopefully pretty good idea from a sample of what these could be. Again, epsilon, we're going to call the error term. It's how far off individuals are from our line, or how far off our line is from the actual observed value, maybe a better way to say that. And it's going to be true for every individual. I'm very, very rarely going to predict an individual's outcome perfectly, but hopefully I am going to get pretty close to the vast majority of people. Now, remember that E of y, this just stands for the expected value of y, or the average value of y. In this particular case, the expected value of y, or what is y on average? Well, y on average, as it relates to x, is going to be that line. So this is going to be the average values across all the people. Note that we don't need an error term because this is on average across everybody. We only need the error term when representing those individual dots and how they differ from that line. So we'll be using this for prediction to predict on average, and we'll be using the previous one just to remind us that our predictions for an individual are going to be a little bit off. Again, this is our line, and actually this is really important to note to what the different components of the model mean. Our beta 0, again, this is the population value. Actually, I'll go on and write out what the sample value is going to be. It's going to be B0 or beta 0 hat. Actually, when I have a parameter, a general way that I can make a parameter estimate, is adding a little hat over it. And then B1, very creatively, is going to go to B1 or beta 1 hat. This is the notation I'll use for my sample. So the stuff in red is what I'll do for the sample when I actually try this out and fit guesses for this value using sample data. The stuff in black is the population value. Okay, but what do these mean anyway? Well, all of these mean the same thing. All of these for B0 or beta 0 are where the line crosses the y-axis. So this is what is my y value, or my average y value, my expected y value, when x goes all the way down to 0. And for beta 1, this is the slope of the line. So as my x increases, does y increase or decrease? So beta 1 is the slope. Now, if you remember back to like high school algebra, I'm sure you made lines, maybe y equals mx plus b. Gosh, I can remember back to what my high school algebra class was, but something like that. So if you've got y equals mx plus b, this is going to be your b, your intercept, and this is going to be your m, your slope, m times x. In statistics, we use beta 0 for the slope and beta 1 for the intercept for the first independent variable. And not to surprise you or throw you for a loop, but we'll have beta 2 when we have an intercept or a slope for a second independent variable when we get to multiple regression. Now, if y increases as x goes up, so x goes up as x going to the right, think about my little cursor moving to the right here. What is y doing as my x goes over to the right? That is, what is happening on my vertical axis? Well, as my x goes to the right, y is going up and up and up and up. So we're going to call that a positive, for an increasing relationship between the two. So we'll say that the slope is positive. Now for this case, we have the exact same meanings of these terms. In fact, we'll have the exact same parameter estimate. Like none of the notation changes depending on the direction of the line, but all that changes is as my x keeps going up and up and up. That is, x moves to the right, x gets higher. What is y doing? Well, as x goes from left to right, I can see that y is going down and down and down and down and down. So this would be a negative or decreasing relationship between x and y. And of course, I can have no relationship between x and y. That is, as x continues to move up, y doesn't change. Note that if as x moves, y doesn't change, this means that the value of y doesn't depend on x. If x moves and y doesn't change at all, well then y isn't really affected by what x is. And if that's the case, there's no relationship between y and x. If x changes and y doesn't, like y is just doing its own thing, it doesn't really matter what value x is, y is just doing its own thing, well then y doesn't depend on x. Again, y isn't related to x. We'd say that there's no relationship between these values, or no linear relationship between these values. Now, I already mentioned that we have the estimated regression. So the hat means estimate. So the estimated y, and actually that's good to write down somewhere, hat means estimate. The estimated y is b0, or you could write beta 0 hat, plus b1, or you could write beta 1 hat times x. And this is our regression equation. This is what we're actually going to fit with our data. We can't ever find the betas, but we can find these b's with data. So we're going to gather data, we're going to fit this to make our best guess, and that's going to let us make our best guesses at y. And that's pretty much the process of simple linear regression. All right, so what does this look like? Well, typically, depending on where I'm at, I might start with my model or start with my data. Typically, you want to start with your model because that tells you what data you need to collect. So I've got an independent variable and a dependent variable I want to study, and I'm assuming that they're linearly related, so that tells me I need a simple linear regression. Then I move on, I get data for the x and y that I need to determine if there's a regression. I fit my best guesses at these values over there. My b0 is a guess for beta 0 and b1 is a guess for beta 1. I didn't just make up these guesses. I used the data to calculate these guesses. And through using that data, I'm hopefully getting a pretty good guess, again, better than I would just make up on my own, as to what these values are. So I have these B0 and B1 estimates for beta 0 and beta 1, and then I can go back and see what those values are. Again, remember, this is my initial question. This is what started everything out, is what's the relationship between this x and this y? Is it linear, etc.? And I can look at that and determine if there is a linear relationship between x and y, and if that linear relationship is positive or negative or otherwise. All right, well, this is pretty much the big picture of what we're going to try to do with the regression. In the next slides, we'll be talking about how we fit these models a little bit more detailed, and how we can interpret these in a little bit more detail too.